Okay, we're going to continue our exploration of multiple integration with the introduction of triple integrals. I'm looking for all of these objectives plus a couple of more that are not listed here. Um, the book doesn't really do this, but this is something that I feel is important. I'm much more interested in you being able to describe the domain and turn that description into limits of integration in a triple integral or in a double integral than I am in you actually being able to grind out the multiple integration by hand. So here, for me, setting up the integral is the most important goal, and then also being able to evaluate that integral with some kind of a computational program is an important goal too. Less important, you need to understand sort of conceptually how to do it and how in very simple cases to compute a double or triple integral by hand, but mostly I'm looking at you setting it up and then jumping over to a computer program to evaluate. Um, so what are the big ideas here? We're just adding another dimension. We've done single integration, right? That was Calc 2. We've done double integration. Now we're just adding that last variable to get a triple integral. Instead of integrating over an area in the XY plane, we're now integrating over a volume in three-dimensional space. And we're going to stop in this class at 3 dimensions, although in more advanced math classes, you can actually integrate as many variables as you like. So there's nothing special about triple integrals. You can have 10 independent variables and be integrating in 10-dimensional space. We're not going to do that here. Of course, the overarching goal of the class is to give you some really useful tools for your physics, your engineering, your chemistry, etc. Applications, and most of those applications occur in both 2 and 3 dimensions. In 3 dimensions here, the integrand is now thought of as a sum of little cubes of area instead of little squares of, sorry, cubes of volume instead of little squares of area. And the integrand in this case is now, in 2D, the integrand was sort of interpreted as the height of some column that was above this little patch in the domain of integration. That's not really what's happening now. Now the idea is that the integrand is maybe the density of some material that this little cube occupies, or maybe it can be a velocity flow if we'll see that in later sections. So it's a little bit more abstract, but if you change the integrand to just the constant 1, then integrating over some volume is going to give you the volume of that integral. The challenge here in this section, it's a very skills-based section. The challenge here is to describe 3D objects mathematically, take those descriptions and put them into limits of a triple integral, and then be able to evaluate that triple integral. Checking in with the section here, as I mentioned, what we're doing is taking an existing volume and subdividing it into lots of tiny little volumes, which we will call dV, or delta V in this case. And delta V is just a small length in the x direction times a small length in the y direction times a small length in the z direction, with the idea that what we've done is we've sort of chopped up this larger volume in the x direction, in the y direction, and the z direction in some uniform way. And of course, the product of those little subintervals gives me the volume of a little chunk of volume, gives me the volume of a little sort of infinitesimal delta V. The triple Riemann sum is going to be summing in each of the 3 directions. We're multiplying these guys together to get the volume of the tiny little cube, and then we're also multiplying by the value of f somewhere inside that cube. It's not really important where inside the cube you're taking the volume of f, because ultimately to get the integral, we're going to let L, M, and N, we're going to let the subdivisions go to 0. and then it won't matter where you've evaluated inside the cube. Taking this limit, we get the triple integral over a rectangular box. Rectangular boxes have that nice feature that the upper and lower limits in all three variables are constants. These are the easiest kinds of triple integrals to evaluate. And you evaluate them in exactly the way that you would have evaluated a double integral in that situation. Let's fly over really quickly example 5.36, where we've got this integrand x plus y z squared, and we're integrating first with respect to x, then with respect to y, then with respect to z. Triple integrals, like double integrals, always work from the inside out. It's just that there are 3 steps now instead of 2. We'll have the inner integral, the middle integral, and then the outer integral. Those are the words that I'll use. The book doesn't use those words. So faced with this triple integral over a rectangular box with these constant limits of integration, we do the inner integral first with respect to x. That means holding all the variables fixed except x and integrating in that variable. Doing so and plugging in 5 and 1 and subtracting, we get the result 12 plus 6yz squared. And now we're ready for the middle integral. The middle integral is with respect to y, so we're going to integrate this thing with respect to y, plug in 4, 2, subtract, and we end up with this outer integral. The outer integral is with respect to z. We integrate with respect to z. We plug in 1, we plug in 0, and we get the final result, 36. So very similar to double integration over a rectangular region, just holding variables fixed, integrating with respect to a single variable until you get a final result. Where this gets interesting is when the shapes are more complicated than rectangular boxes. So let's move forward to that. So triple integrals over a general bounded region. The idea being that one or more of the sides of the region is curvy. It's described by some surface, some function of 2 variables. And like we saw in when we were integrating double integrals, when we were doing double integrals over general regions, in that situation, some of the sides of the region were described by functions, either of x or of y. Now we're going to be describing some of the sides of the volume by functions of x and y, or functions of y and z, and so forth. A little bit more complicated. However, if you just follow the process of first figuring out what the order of integration is, and then figuring out from the inside out what the limits of integration are in each of the variables, you'll be fine. That said, it does require a lot of practice, so I want you to work a lot of the exercises at the end of the section. Okay, a triple integral over a general region is going to have variables in some of the inner integrals. So for example, in this case, you've got some region in the xy plane, and then the z variable is sort of ranging between a lower surface u1 and an upper surface u2. What does that look like as an integral? You integrate with respect to z first, and you use those variable upper and lower limits in that inner integral. And then once you're finished with that, you're left with a double integral that you know how to do. Now, there are, of course, all the possible permutations of these situations. So maybe the y variable goes from a surface on the left to a surface on the right. Maybe the x variable goes from a surface in the back to a surface in the front. And it's up to you to kind of figure out what's the most strategic way of arranging these integrals so that I can describe my, my limits as easily as possible and actually carry out the integration. You're going to find that it might be strategic to use one order of integration over another. Some integrands are easier to integrate in some orders than in others. And these are all things that I expect you to sort of figure out as you work through the exercises at the end of the section. Okay, so let's talk about evaluating a triple integral over a general bounded region. So here we've got some integrand. We don't really care. It's 5x minus 3y. It could be anything. And we're integrating over the solid tetrahedron. If you don't know what a tetrahedron is, it's a 3-dimensional space or 3-dimensional set with 4 vertices, flat faces with 4 vertices. So that's what we see here. This is a 3-dimensional object with 4 vertices. The 3 here that we're seeing in the foreground, and then the 1 in the back at the origin. Three of the faces of this tetrahedron are just coordinate planes, and those are easy to describe mathematically. X equals 0, y equals 0, z equals 0. Those are the coordinate planes. The slanted face, the fourth face of this tetrahedron, is described by a plane, x plus y plus z equals 1. What we're going to do is set up the integral where we're integrating in the z direction first, and then in the y direction, and then in the x direction. Once we've chosen the order of integration, it's up to us to figure out what the limits of integration are going to be. So when we say we're integrating, the inner integral is with respect to z, we're doing the integral with respect to z first. We need to find descriptions of the beginning and ends of line segments parallel to the z-axis and inside the volume of integration. So in this picture, that's described by a vertical line always starting on the xy plane and always ending on this slanted face. If we always start on the xy plane, that means z starts at 0. And if it's going to end on the slanted face, what we have to do is solve for z in terms of x and y. Doing so, a vertical line, or in the z direction, a line that's parallel to the z-axis, always starts in the xy plane, z equals 0, and always ends on the face, the slanted face of the tetrahedron, which we can describe as z equals 1 minus x minus y. So that inner integral with respect to z has limits 0 and 1 minus x minus y. Once we've figured out what those limits are, we take this shape and we smash it into the remaining plane. So in this case, the remaining variables are the x and y variables. We smush it down into the xy plane, and you can imagine that this is going to squash down into exactly this triangular region that corresponds to this lower face of the tetrahedron. Now you make a decision again, which variable am I going to integrate with respect to? Here we're going to integrate with respect to y. We could just as easily have integrated next with respect to x, but we'll respect the order of this example and integrate with respect to y. When we're integrating with respect to y, we're looking at line segments that are parallel to the y-axis. Those line segments always start here at y equals 0 and always end on this slanted face, this line, which we determined to be y equals 1 minus x. How do we figure that out? Well, down here on the xy plane, we know that z is equal to 0. So in this full equation of the plane, z is equal to 0. And we have 0 equals 1 minus x minus y. Solving for y in that context leads to y equals 1 minus x, and that's how we figure out the upper limit of this region of integration, or of this variable of integration. Doing so, the middle integral is with respect to y. We go from 0 to 1 minus x. Once we've figured out y, we smash that domain down onto the last remaining variable, which in this case is the x variable. And that clearly covers this orange line segment, which lives between 0 and 1, and that determines the limits of integration in the outer integral, the last variable x, 0 to 1. Once you've set up the integral, which is like 90% of what I want you to get out of this section, you can begin to integrate. You integrate with respect to z first, and you see there's no z here, so that's a pretty easy integration. You plug in z, plug in the top, plug in the bottom, subtract, integrate with respect to y, integrate with respect to x, and when all is said and done, you get 1/12. Alternatively, you can jump over to Sage and plug it in over there, or your favorite other computer program that does integration. Okay, the rest of this section is really examples. Finding volume by integrating a triple integral. If you want to find the volume of any particular shape, it's up to you to first describe the shape as limits of integration, and then just set the integrand to 1. When you integrate 1 dv, what you're really doing is computing the volume. You're adding up all of the tiny little dv's over the region. They net out to the full volume of the figure. So you can look at that example. Changing the order of integration is very much like changing the order of integration in 2D. You have to go back to the original shape and rethink every step. So up here, we integrated with respect to z first. We could have chosen to integrate with respect to y first. In this case, line segments parallel to the y-axis would always start on this face in the xz plane and end on the slanted face. That would require us to start y at 0 and end on the equation of this plane, which would mean we would solve for y in terms of x and z. Y is equal to 1 minus x minus z, and so the limit of integration in the y direction, if you were doing that first, would go from 0 to 1 minus x minus z. You have to rethink all three limits of integration to change the order of integration, and I promise to do an example of that as well. The average value of a function in 3 variables is very similar to that of 2 variables. The only difference is once you've done the integral, you divide by the volume of the region that you integrated over instead of the area of the region that you integrated over. Other than that, everything is the same. Okay, we are now at the exercises. A few words about the exercises here, and I'm going to put some notes in the corresponding Canvas discussion here. In my opinion, these exercises are not super well written for this particular text. We have to remember that this is an open source textbook. It's community developed for free by a large collection of individuals, and it's a relatively young textbook. So what I'm asking for is your indulgence, your patience with these exercises. Most of them set up relatively well. Few of them evaluate very well. Most of them are just really ridiculously complicated to evaluate by hand. That's okay because mostly I'm emphasizing that you set up and then take it over to a computer to evaluate. I want you to try to evaluate some of these by hand, some of the simpler looking ones, but don't dwell on really complicated long calculations. That being said, the first one I want to talk about is exercise 188. So let's hop over to the notes and look at exercise 188. In this example, you're asked to change the order of integration by first integrating with respect to z, then x, then y. You're not explicitly asked to do this integral, but I'll do it anyway just to get our feet wet. You'll notice that working from the inside out, the order of integration is x, then y, then z. And you're asked to change it to inner z, then x, then y. So to remind myself of that, I'm going to set up the whole integral. And by Fubini's theorem, we know that it doesn't matter if we change the order of integration, as long as we're careful with the limits of integration. And for some reason, my pen is going very slowly at the moment. Hopefully it'll speed up. You know what, I'm going to close OneNote here and reopen it and hope that it improves. All right, let's see if that's helped. So we're asked to integrate a triple integral, and apparently it hasn't helped. So let's just see if it picks up in a minute here. And we're going to go dz, dx, dy. No, this is just too slow. I'm going to pause and restart here. All right, let's see how the reboot has done with our slow pen. It's getting kind of messy in here. Let me just check this right here. That looks much better. All right, cool. Let's get rid of this and just kind of start over again. So we're going to write out the triple integral and we're going to save the limits for the end. The integrand doesn't change when you change the order of integration, so it's x plus y over z. First with respect to z, then x, then y. So from the inside out, like that. So now if we're going to integrate with respect to z, we need to identify the z limits. This is a rectangular box, so the limits of integration are all constants. So this is the one time where when you're changing the order of integration, you don't have to worry about anything. You can literally just swap the limits. So it's really just a matter of figuring out which of these three sets of limits corresponds to which of these three sets of variables, or three variables. And it's the outer integral that corresponds to z, and we're moving that to the inner integral. So that means these outer limits, 1 to 2, have to go to the inner limits like that. Next, we have dx. dx in the original integral is the inner integral. Those limits were 0 to 1. Now it's the middle integral. And finally, dy. In the original integral, dy was the middle integral. That's the middle set of limits, -2 to -1. You're not asked to actually calculate this integral, but let's do so anyway. I want you to, when you're doing integrals either on a computer, triple integrals either on a computer or by hand, I want you to kind of follow my example here. We do the inner integral with respect to z, and that is going to be x plus y times the natural log of z from 1 to 2. Those of you from Calc 2 might remember that it should be the natural log of the absolute value of z, but since the range of z values is positive, we don't need to worry about the absolute value. X plus y times the natural log of 2 minus the natural log of 1. And recall that the natural log of 1 is 0. And so the inner integral is just this constant natural log of 2 times the expression x plus y. Now we move to the middle integral. In the middle integral, we are integrating with respect to x. The constant natural log of 2 just goes along for the ride. We get x squared over 2 plus xy. And the limits of integration in the x direction are from 0 to 1. Plugging in 1 and plugging in 0 and subtracting, plugging in 1 we get 1/2 plus y. Plugging in 0, since there's an x in both terms, those are both wiped out. And last, not least, the outer integral. The outer integral is with respect to y. The natural log of 2, again, is just going along as a constant. We get y over 2 plus y squared over 2, like that. And we're going to plug in -2 and -1. Plugging in -1, so the natural log of 2 going along for the ride. I'll put a big square bracket around there. Plugging in -1, -1/2 plus 1/8 minus the quantity, plugging in -2, that's -1 plus 2. And let's simplify. We've gone this far, we might as well simplify as much as we can. What do we have here? We have a 1 and a -1/2, so that's a plus 1/2 plus 1/8. So what's that? 5/8 plus another, or minus a -2. Sorry, -2. That is 16/8. So what's that going to work out to be? Negative ln of 2 times 11 16ths, I suppose. Let me think about that. Sorry, 11/8. Right, because 2 is what? 16/8. 5 minus 16 is -11. So final answer, right there. A nice exercise might be for you to change the order of integration again to one of these other ones and confirm that you get minus natural log of 2 times 11/8. In fact, let me check my notes here to make sure that that's what's happening. Oh, okay. Seems legit. Okay. All right, in problem 194, you're given a more general region of integration. This is a region that is not just a rectangular box with constant limits of integration in each of the three variables, but in fact there's some variation in one of the directions. I'm a creature of the plane. I'm not a very good artist when it comes to sketching these things in 3 dimensions. So what I tend to do, and if you also feel like you're in that same sort of non-artistic boat, I tend to just focus on a plane and then imagine what's going on in the 3rd dimension as I build these integrals. So the plane that I'm going to focus on is the XY plane. I'm going to try to understand the XY plane, and then I'll just tack on the Z in my imagination. Why am I choosing the XY plane? Because that's where we're most comfortable, and the Y variable is complicated. So let's give ourselves an XY plane to work with, like this. And what we see is in the Y direction, let me label my axes here. In the Y direction, we are moving from a parabola opening down to a parabola opening up. And I'm going to blow up my scale a little bit so that my parabola kind of goes through here and here. This is the upper parabola. And the lower parabola is going to kind of go through here and here. Again, it's always a good idea to sketch these things. So another thing that I'm going to do is I'm going to introduce some color coding. X is red, Y is going to be green, and Z is going to be blue. This is consistent with the GeoGebra axes, if you'll remember those. All right, so what we see is in the Y direction, we're moving from the lower parabola to the upper parabola. That's what we're always doing. On the other hand, we've got x between 0 and 1. So we're only doing this along this line segment right here. So generically, we're looking at something like this. And the last line that'll be is for x equals 1, and the first will be here, and then all of the lines in between. So we can actually do this integration. Oh, sorry. What does the volume look like? So the volume is made up of all of the sort of line segments that start on the XY plane inside this region, not this region here. Let me get rid of that. All of the vertical lines parallel to the Z-axis, which is coming out towards you, over this region. All right, so let's pick an order of integration. It's necessary that we do this variable as either the inner or the middle integration. We can't have variable limits of integration as the last integral. That's not these functions, because those variables never get resolved as you go through the integration, and it's important that all of these variables sort of get mapped to their particular ranges. So not super important the direction that we're going to go here, but let's say just for the heck of it, we'll do dy dx dz, dy dx dz. And the integrand here, I'm just going to call this f right now for the sake of writing, because again, we're really emphasizing these limits of integration, not so much the execution of the integral. All right, so the inner integral is y. It starts at minus x squared and goes up to x squared. Once we've accounted for that, what we're going to do is we're going to take this region of integration and smash it into the xz plane. And this might help you visualize a little bit what's going on. So we take this region of integration, and now we look at the x, z plane. We've accounted for y. Well, can you imagine where this lives? This is a cylinder whose base is sitting in the xy plane, and that goes up to the plane z equals 1. And if you looked at it from the side, right, it would really just look like a rectangle on that side, and it goes up to z equals 1. Let's find z equals 1. That's going to be in blue. So if you took this figure and you smashed it into the x, z plane, you would get this rectangle. All right, we've decided somewhat arbitrarily to integrate with respect to x now. What does x do inside of this region? X we're going to represent by vertical lines parallel to the x-axis, parallel to the x-axis. Those lines parallel to the x-axis always start at 0 and always end at 1. So those limits on x are going to be 0 to 1. Once we're finished with that, we can collapse this domain onto the z-axis, the remaining variable, and we see that it's going to cover the interval from 0 to 1, and that's the last set of limits, 0 to 1, like that. So it's always this process of building the three-dimensional space, dealing with one variable, collapsing it onto the remaining plane, dealing with the next variable, and then collapsing it onto the remaining variable. All righty now, how do we evaluate this integral? This is actually non-trivial. So what I'm going to do is show you my practice, which is to jump over to some computer program to evaluate these integrals. And I've got Sage up and running over here. And we're going to be working with the variables x, y, and z. So I'm going to declare those variables. And then I want you to, if you're using Sage for this purpose, I want you to kind of match my process here. So I'm going to do the inner integral first, and it's just a collection of integrate commands. I want to integrate x times y plus y times z plus x times z. And I want to integrate that with respect to y first. And the lower limit is x squared, and the upper limit is the lower limit is minus x squared and the upper limit is x squared. And once I'm finished with that, I want Sage to show me the result. So I'm just going to put show inner right here. Takes a little bit. And as you can see, a relatively complicated polynomial in x and z. Let's continue. The middle integral, again, we integrate. What are we going to integrate? We're going to integrate the inner integral with respect to what variable? With respect to the x variable. Over what range? 0 to 1. And then I'm going to ask Sage to show me the result. That simplifies rather nicely, z over 2. And in fact, the last integral is one that you could probably do by hand, but just to finish this off, outer is going to be the integral of middle with respect to which variable? Z over what range? 0 to 1. And I'm going to ask Sage to show me the result. And this will be the final answer, 1/4. So I can just put 1/4, and I'll just put a note here using Sage. All right, let's carry on. In exercise 212, you're not only given a description of the bounds of the solid that you're integrating over, but you're actually given a figure as well. So you're asked to evaluate this integral. The integrand is x, y, z, whatever that means. Again, we're not super concerned about these integrands at the moment. We're very interested in being able to generate good limits of integration. All right, what we see here is in the x direction, lines within this figure that are parallel to the x-axis are always starting on this front face and ending on this curved surface. So we could do that. On the other hand, we already have y is equal to the square root of x, so maybe we'll go in the y direction because y is already expressed in terms of x. In the y direction, a line that's parallel to the y-axis is always starting on this back face and ending on this curved surface. The back face has equation x equals 0, right? Sorry, y equals 0. We're doing y. And the front face is y equals the square root of x. So that seems pretty straightforward. So let's decide right now that we're going to go y and then x and then z. Let's do y, then x, then z. So that means the inner is with respect to y, the middle is with respect to x, and the outer is with respect to z. Again, I'm just going to write the integrand there. We'll deal with it later. All right, in the y direction, we are starting on this back face. That back face is y equals 0. And ending on the front face. The front face is y equals square root of x. So that's the upper limit of integration. So we've accounted for all of the integration in the y direction. What do we do now? We collapse this figure into the remaining plane, the variables that remain. So this collapses into the xz plane. And can you see what it looks like in the xz plane? If you take this and collapse it, you get a nice simple rectangle. The base goes from 0 to 4, and the height goes from, it looks like -2 up to 1. So if we collapse this figure into the xz plane, what we get is, I'm just going to draw these in without really caring much about scale, -2 and 1 up here like that. We're going to get a rectangle that looks like this. All right. So if I were to collapse this figure into the xz plane, this is what I would see. This is nice. This is just a rectangle. So let's do the limits of this rectangle. In the x direction, we're always starting at 0 and going up to 4, and that's the next integral. And then finally, in the z direction, what do we do now? We collapse this domain onto the z-axis, the last variable. And we have -2 to 1, like that. Now you are asked to actually integrate this figure, so we can jump over to Sage again, and let's just practice that inner, middle, outer paradigm that I showed you. So for this example, the inner integral is x times y times z. And which variable are we integrating with respect to? Oops, I forgot my integrate command. We are first integrating with respect to y. The lower limit is 0 and the upper limit is the square root of x, like that. And then I'll show that result. It's not necessary that I show this result. I'm just kind of giving you a practice here. And let's do all of this at once. The middle integral is the inner integral with respect to x from 0 to 4. And let's show the middle. And finally, the outer integral will integrate the middle integral with respect to z, and that goes from -2 to 2. Sorry, -2 to 1. And let's show that result. So in this case, all we really care about is the outer. So we can see these intermediate results. If you were to do this by hand, this is what you would get for the inner. This is the middle. This is the outer. In fact, this looks like it wasn't that complicated, and maybe this is a good one to practice by hand. Net result, minus 16. All right, let's do another. Okay, here you're given an integral, and you're not given the shape. So the only way that you have of sort of figuring out what this shape looks like is to look at these limits of integration and the order of integration and try to piece it together. So it says use a computer algebra system to graph E and to find its volume. So we'll do that. We see that Z goes from 0 up to this shape. Let's use GeoGebra to get a grip on what this looks like. So we'll fire up GeoGebra and run the 3D calculator, and we'll just plot all of the various surfaces. So Z equals 0. GeoGebra happily gives you this plane right here. And Z is going to also go up to 1 plus the square root of x squared plus y squared. I think that's it. Yes. Okay, so you can imagine that in the z direction, vertical lines that are parallel to the z-axis always start here at 0 and always end up here on the surface. And what describes the surface at that point? This equation. So we've got a good idea about how z integrates. The next step is to see what's going on in the y direction. So y is always starting at 0 and ending at minus x squared. So let's just see what that looks like. Y equals 0. So remember, y is parallel to this green axis, and we're ending on y equals minus x squared. All right, so we've got a little bit more information now. Y always starts on this vertical plane at y equals 0 and always ends on this sort of parabolic cylinder, the red shape. Okay, what's Z doing? Just as a reminder, Z is starting down here at the bottom and going up to the surface. What's Y doing? It's starting on this plane and going out to this parabolic cylinder. Last, not least, what is x doing? X is going from minus 1 to 0. So let's look at x equals minus 1, yet another plane. Where is x equals minus 1? So here's the x-axis, the red axis, and here's minus 1, and we can see the new plane here is this guy. And going up to x equals 0, okay, so we have now enclosed a volume. It's not entirely obvious where that volume is. It's very difficult to see. That volume is between these two planes, x equals -1 and x equals 0. It's between y equals 0 and this parabolic cylinder, and it's between z equals 0 and z equals the cone. Very challenging to see where that is. It's kind of tucked in here, and you just kind of have to imagine that it's in there. It's inside here, and then it's below the blue cone and above the XY plane. Very challenging to visualize. And then find its volume. So round your answer to 2 decimal places. So you're not being asked to actually do this integral. In fact, this would be a challenging integral because when you integrate with respect to z, the middle integral is going to work out to just this upper limit. And then you're going to have a hard time integrating this with respect to y. You're going to have to use a trig substitution. So better to not worry about that and just jump over to Sage and go through the process again. I'll repeat my paradigm here. We're going to integrate. Okay, and we're asked to find the volume, which means we're integrating the constant 1. So we're going to integrate 1. And we're going to first integrate with respect to z from 0 up to 1 plus the square root of x squared plus y squared, like that. And then I'll just show that result, just because you might be interested along the way. Let's do the middle. In the middle, we're integrating the inner with respect to y from minus x squared up to 0. Alrighty. And we'll show that result just because we might be curious. And last, the outer. That's the integral of the middle with respect to z. And z is pretty simple. With respect to x. And x is pretty simple. It goes from minus 1 up to 0. And let's show that result. Sage has to work a little harder here. In fact, looks like I made it work too hard, and see if I can figure out what the problem is. This integral was so hard that it was asking if you were willing to assume that x was positive. And the short answer is, looking at this figure, we can't really assume that x is positive here. So let's check something here. If we go back to this figure, remember what was happening here? X was going, so x is the red axis. It was going from minus 1 to 0. By symmetry of this figure and symmetry of the cone, the volume is going to be the same if I go from negative 1 to 0 or if I go from 0 out to 1. So what I'm going to do is say, hey, you know what, Sage, I can actually do that for you. So I'm going to plot that. And just noting the symmetries here, I know that that volume is going to be the same. So let's go back over to Sage and see if, having made this realization, oh gosh, what am I doing here? Yes, there we go. That I can actually keep x positive and get the same answer. So let's try that. It's still not happy, right? Is x 0 or non-zero? It's still not happy. It's wanting me to make this assumption. What's going on here? Behind the scenes, Sage is doing a really hard integral. Remember I said that there was probably going to be some kind of trig substitution in there. So Sage is trying to do that substitution, and it's worried about the sign, S-I-G-N, of x. So let's do it the favor that it's asking for and assume that x is positive and see if we can get a result. Yeah, and see, we're getting this weird function r sine arc. So this is the arc hyperbolic sine function. So there's clearly some crazy stuff going on in the background here. So Sage was able to figure this out by adding this assumption, and it gave me this crazy number here. Let's turn that into a decimal because that's what's being asked for. Capital N is the function that turns anything into a number, and we'll feed it the outer. And it's going to go ahead and figure out what this is as a fraction, and to 2 decimal places, this integral is equal to 0.61. So not much work here. I can just say by Sage, this is about 0.61, and then GeoGebra for the visualization. All right. So in problem 216, this is another exercise in changing the order of integration. And we see this sort of weird notation. A circular permutation of x, y, and z is the arrangement of the numbers in one of the following orders. X, Y, Z, the first permutation would be to take this x and move it to the end. So you get YZX. And then continuing, take the y and put it in at the end, and you get ZXY. And then in fact, you can go ahead and do the last, circular permutation, put z at the end, and you're back to XYZ. So this is asking for a circular permutation of this ordering. The circular permutations, the first circular permutation is going to be take y and put it at the end, dx, dz, dy, and the second circular permutation will be to take x and put it at the end, dz, dy, dx, like that. And then of course, if I were to do the last circular permutation, move the dz to the end, I would be back where I started. So that's what they're talking about with these circular permutations. Not super important to this problem or even to Calculus 3, but a nice little mathematical tidbit. So you're asked to actually do new integrals for both of these circular permutations. So let's do the integral for one. As always, when you're changing the order of integration, whether it's 2 dimensions or 3 dimensions, you have to get a good understanding of the region of integration. So the first thing we're going to do is sketch this region of integration. I, again, like to work in the XY plane and then figure out what's going on in the last dimension in my mind. So I'm going to just work in the XZ plane, in the XY plane here, like this. And what's y doing? Y is, of course, these are line segments that are parallel to the y-axis. They're going from 0 to 1 minus x. What does 1 minus x look like as a line, right? Y equals 1 minus x. That's a line with a y-intercept of 1 and an x-intercept of 1. So that's actually this line, and in keeping with my notation, that's that line. And then y equals 0 down there. I'm sorry, down here. Right, any point along here. So we would be cutting in slices along the y direction like that. All right, what's x doing? X is between 0 and 1. So what we're looking at here is this region inside this triangle. And then finally, what's z doing? Z is going from 1 to 3. So you can imagine sitting up above this region in the xy plane is the horizontal plane z equals 1 and the horizontal plane z equals 3. So this is a cylinder with a triangular base that's shifted up 1 unit above the xy plane and extends up to 3 units above the xy plane. So you can imagine that third variable. All right, well, the first task here, the first circular permutation, is to figure out what's going on in the x direction. So we're going to build this integral. Again, I'll just call the integrand f. And we're going to go dx, dz, dy. Dx, dz, dy. Dx means we're going to build little horizontal lines that are parallel to the x-axis like that. Any horizontal line in this domain is going to start at x equals 0, and it's going to extend up to the equation of this line. The equation of this line is y equals 1 minus x. Of course, we need to solve for x. Doing so, we get 1 minus y. X equals 1 minus y. Okay, so we've accounted for the x variable. The next step is to take this figure and smash it into the xz plane. So let's look at that. In the xz plane, xz, like that. I'm sorry, smashing it into the YZ plane, Smashing this figure into the YZ plane, we know that Z starts at 3, it starts at 1 and goes up to 3. And what does this thing look like from the side if you're looking at it from down the x-axis? It's actually just tracing out a rectangle like that. Okay? And I guess if I'm going to preserve scale here, y goes from 0 to 1. So let me fix that for you like that. Okay, so that's what it looks like from the side. We're supposed to do z next. An arbitrary vertical line in this domain goes from 1 up to 3. Once we finish that, we smash it down onto the y-axis, which we're going to paint in green. If we smash this down onto the y-axis, it's going to cover the interval from 0 to 1, like that. So that would be the integral in the first circular permutation. Let's do the second circular permutation. All right, in the second circular permutation, we're doing dz, then dy, then dx. dz, then dy, then dx. Honestly, if we look at this figure, z is still going to go from 1 to 3. So dz, dy, dx, like that. Z is going to go from 1 to 3. Now if we take that figure and we smash it down into the remaining variables, in other words x and y, what do we get? We get this figure, the one that we sketched in the first part. And if we want to know how y moves, lines parallel to the y-axis are going to always start at 0, and they're always going to end on the line y equals 1 minus x. And then finally we take this and we project it or smash it into the remaining variable, which is x, and that's going to cover the interval from 0 to 1. And then we're going to integrate f like that. And that's it. So compare these two integrals. Notice that the upper and lower, the upper limit here changed a little bit, and there's not a nice recipe. You always have to go back to the original domain and figure out what it's going to look like, sort of how to kind of redo the limits. I'll leave it to you to go over to Sage and figure out what this integral actually evaluates to. This looks like one that you could do by hand also, and it might be a useful exercise to confirm Fubini's theorem here and maybe show that these three integrals are all the same. All right, in problem 226, you're asked to think about a pyramid with a base that's square like this and a vertex at 0, 0, 9. As usual, I'm going to just mostly live in the XY plane and imagine the last dimension. This pyramid has a base that sits on the interval -3 to 3 cross -3 to 3. So from -3 to 3 here to here in the x direction, and -3 to 3 here and here in the y direction. And we can connect those dots like that. That's the base. And then what you can't see here, here's the x-coordinate, x-axis and the y-axis, is it goes up to a peak here at the center, at the origin, and that peak is 9 units high. So here we're looking down on top of this this square-based pyramid. The book, there's a typo here. The book says, show that the equations of the planes of the side faces of the pyramid are given by these. Only one of these is correct, and we'll see which one of them is correct in a moment. The rest of them are all just typos. So I've sent a correction into the textbook authors. Hopefully it'll be fixed in the near future. The four faces that we're interested in, or the side faces, are the slanted faces. So there's the bottom face, which is the square sitting on the XY plane, and then the four slanted faces that come together at the peak at the top. Let's look at just one of these. Oops. Yes, 3 and 4. Let's look at the first one. So this goes way back to maybe the second chapter that we studied for equations of lines and planes. We want to find the equation of the plane for this face, the face right here. How are we going to do that? Well, we know three of the points on this plane. We know that this point is actually 3, 3, 0. We know that this point, the peak, is 0, 0, 9, and we know that this point is actually 3, negative 3, 0. Given 3 points, as a bit of review here, you should be able to compute the equation of the plane that contains those 3 points. Let's do that. We're going to compute, first of all, the displacement vector from this point on the base up to the peak. That displacement vector is going to be 0, 0, 9 minus 3, 3, 0. Doing that subtraction, we get the vector negative 3, 9. And since we only care about the direction of this vector, we can move quickly to 1, 1, negative 3, like that. And let's get this other vector, this other displacement vector, which we can compute again by taking 0, 0, 9 and subtracting this point 3, negative 3, 0. This results in the displacement vector negative 3, 3, 9, like that, which again we can, since we only care about the direction, we can knock this down to 1, negative 1, negative 3, dividing out the negative 3. We have two vectors now that are parallel to this plane that we're interested in. How do we find the normal vector? You guessed it, cross product. So let's compute the cross product. This will be the normal vector to the plane. And we'll blot out the first column and do negative 3, minus 3, so that's negative 6. And I'll move on to the middle here. We get negative 3 minus negative 3, that's going to be 0. And last, we get negative 1 minus 1, that's negative 2. And we can simplify this a little bit by dividing by negative 2. We get 3, 0, 1. That's the normal vector. The equation of the plane is this normal vector, 3 times x plus 0 times y plus 1 times z minus 9 equals 0. That's the equation of the plane. We can, of course, get rid of the 0 times y, and we get 3x plus z minus 9 equals 0. Or alternatively, 3x plus z equals 9. And that is this face. Now, do we have to do all of this work to find the other 3 faces? The answer is no. On the other hand, if you want to do that, you can certainly try to figure that out. What I'm going to do now is go and try to figure out what I can do. I know that the remaining 3 planes are going to look something like this, probably with a sign change. So what we need is to figure out how we would tweak this to maybe satisfy the second plane. So the second plane, if you plug in 330, you get 3 times 3 plus 0 equals 9. Yay, that checks out. And if you plug in 0, 0, 9, which is the point at the peak, you get the right answer again. What happens if you plug in this point over here? This point is negative 3, 3, 0. That might not work out so well. You plug in negative 3 here and you get negative 9 plus 0 equals 9. Doesn't check out. See if we can come up with a formula that'll work in all three of these cases. And the formula that I'm going to suggest is, oops, hold on for a second. Okay, so how are we going to tweak this to make it fit these 3 points, the 3 vertices of region 2 or plane 2? Well, let's try changing this x to a y. So we'll try 3y plus z equals 9. Why did I choose that? Well, notice what's happening here in the first on the first surface. The x-coordinate is positive, 3, 3. If you look at the y-coordinates along this face, the y-coordinates are positive. So all things being equal, we should just be able to change this x to a y and get what we want. So if you plug in the 3 points again, 0, 0, 9, you get, that checks out. You plug in 3, 3, 0, that's going to check out. And then plug in negative 3, 3, 0, that's going to check out. So that's the sort of the thing that's going to work for the second not the quadrant, but the second face. Let's talk about the third face. All right, in the third face, you're now sort of the reflection of the first face. And the only real difference there is instead of this face having these 2 points at plus 3 for x, they're down here at minus 3 for x. So how might we tweak this to get something that satisfies the third face? Let's try minus 3x plus z equals 9. And we go around and we test these points again. Here, this point is going to be a negative 3, 0. And you plug those in and it all works out. And you probably can now guess that the fourth face is going to be minus 3y plus z equals 9. So these are the 4 equations of the 4 faces, and you can see that the textbook here is just grievously wrong. 3y plus z, that's the second face. Negative 3y plus z, I guess, would be the fourth face. They didn't even, these just don't do anything for you. So so show that the equations of the planes of the side faces of the pyramid are blah, 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 and blah. That's just wrong. I've reported it. And these four are the correct. So this one, this one, this one, and this one. All right. Now, find the volume of the pyramid. The volume of the pyramid is really just integrating, it's performing some triple integral of 1 dv. And what we need to do is find some region that's going to give us the volume of this pyramid. Now, it would be a lot of work to go around and do all of these integrals because when you're integrating in the z direction, depending on where you are in the base, you're going to be going up to a different face. So instead of trying to build one integral that sort of does all of this work, let's focus on just one piece of the pyramid and use the symmetry to get the final result. If we look at region 1 here, or face 1, and we look at its projection into the XY plane. And in fact, if we just look at the part of that face that sits above the first quadrant in the XY plane, we can compute the volume of that pretty easily because we know the equation of this side of this face, and we know by symmetry that the volume under this part of the surface is the same as it is here, 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 all the way around. How many slices or chunks of the pyramid are there that look like this piece up here in the first quadrant? There are 8. So what we can do is figure out what that volume E looks like and then multiply the result by 8. So focusing on just the volume under this face in the first quadrant, let's do this integral. In the first quadrant, so let's just get rid of all the clutter and look at the first quadrant. That's something like this. And there's 3, and there's 3, and there's this bit here, and all we really care about is this region in the XY plane, right? Okay, let's integrate with respect to z first, dz, then we'll integrate with respect to y, and then we'll integrate with respect to x. Why did I choose z first? Because I'm going to go line segments that are parallel to the z-axis. The bottom of such line segments always starts at z equals 0, and the top always goes up to the equation of the plane representing this face. That's the first one that we came up with, 3x plus z equals 9, or solving for z, 9 minus 3x. All right, let's do y. So now we have dealt with the z coordinate. We smash that volume down onto the xy plane, and we build limits of integration in that direction. Y, we'll look at line segments parallel to the y-axis. Those line segments always start at 0, and they end on this line. What is that line? You might notice it's the line y equals x. So y starts at 0 and ends at the line y equals x. We've now accounted for the y. The last variable, take that area and smush it down, onto the x-axis, the last remaining variable. And we see that that's going to go from 0 to 3. Oops, I should stick with black. 0 to 3, like that. And I think we're good. Okay. So this is an integral that I think we can do by hand. It's relatively simple integrand. So let's just, for the sake of practice, do this one by hand. The inner integral is with respect to z, and we integrate from 0 to 9 minus 3x. So the inner integral is just 9 minus 3x. How do I do that so quickly? Well, if I integrate dz, if I integrate 1 with respect to z, what do I get? I get z. I plug in the top, 9 minus 3x, plug in the bottom, 0, and subtract, and it all nets out to just 9 minus 3x. What's the middle integral? Well, we take the inner integral and we integrate it from 0 to x with respect to y. Another relatively easy integral because the integrand has no y's in it. So it's a constant with respect to y. We integrate and we end up with 9 minus 3x times x. That's what we get when we plug in y equals x and y equals 0 and subtract. Finally, the outer integral. The outer integral is with respect to x, so we're integrating from 0 to 3 of 9x minus 3x squared. I just distributed that x into the integrand. That's 9 halves x squared plus x cubed, minus x cubed, and we're going from 0 up to 3. It remains to plug in 3 and to plug in 0. Let's do that. 9 times 9 over 2 minus 27. So that's what, 81 halves minus what, 54 halves? And then 81 minus 54. Oh, good Lord, that's going to be 27 halves. And we're done. So now we have to be careful. We're not quite done. That's the volume of just the piece of this square-based pyramid that sits above this region in the xy plane. By our symmetry argument from earlier, we need to multiply that by 8. And so the final volume is 8 times 27 halves, aka 4 times 27, aka 108. 108. Final answer, 108. All right. A little bit more abstract, but a similar kind of problem. Show that the volume of a right square pyramid of height h and side length a is given by this formula. So I'm going to try my three-dimensional artistic techniques here. So we have a right square pyramid of height h and side length a. Something like that. And then the height, this is terrible, but the height is h and the side length is a. All right. Let's see if we can't turn this into a problem similar to the one that we just explored, except now we have variables instead of numbers. I think it's probably wise to situate this thing at a over 2 and minus a over 2 and a over 2 and minus a over 2. Why did I do that? If you look carefully at the length of this interval, it's a over 2 minus negative a over 2, aka a. And if we fill this in, we see that the base of this pyramid is going to have side length a. And then we're not going to try to sketch it in, but here at the point, the tip, the height is h. So let's go through this same process again, but instead we'll do it with these variable sides. All right, let's repeat this. Let's find the equation of the plane of this face. We know that this point is a over 2, and the height is 0. This point is a over 2 minus a over 2 and 0. And this point here is 0, 0, h in 3 dimensions. Let's go through the process again. We'll get these two displacement vectors. This displacement vector is going to be 0, 0, h minus a over 2, 0, which turns into the displacement vector negative a over 2, and h. And I'm going to clean this thing up because remember, we only care about the direction of this vector, not the magnitude. I'm going to multiply through by negative 2 over a, which yields 1, 1, and negative 2h over a, like that. Let's do the other displacement vector, which I'll paint in, say, blue. For that one, same. The tip is 0, 0, h. The corner is a over 2, negative a over 2, and 0. Subtracting, we get negative a over 2, and h. Transforming it so that it's a little bit simpler, I'm going to multiply through by, let's say, 2 over a. So I get -1, 1, and -2h over a for that displacement vector. Now we need to find the normal vector of the plane, so we'll call that little n, and we will write it as the cross product of these two vectors. In the first coordinate, we have -2h over a minus -2h over a. That's going to net out to 0. In the second coordinate, we have -2h over a, plus minus 2h over a, so that's going to be what? Minus 4h over a, or don't forget the minus sign, so 4h over a. Let me just think about that for a moment here, make sure I didn't introduce too many minus signs. I think we're good there. And then last, we have 1 minus -1, 2. I'm a little bit leery of why that x coordinate is 0. See if I believe that. I guess I'm okay with that. Wow, I just don't like that. Let me think about that for a minute. Okay, I just went through that calculation again, and I made a mistake right here. I multiplied this vector through by 2 over a, so that got me -1 and a 1, and that should get me a positive 2h over a. So let's go fix that. Change that to blue, 2h over a, and let's redo this cross product. Apologies. All right, doing this cross product again, we get 2h over a minus -2h over a, so that's going to be 4h over a. The middle one, we get 2h over a minus 2h over a. That's going to be 0. I feel good about that one. And then finally, we have 1 minus -1 or 2. I like that. Now, why do I feel good about 0 in the y coordinate? We're talking about the normal vector to this surface. This surface is sort of slanted, not towards, not above the x-axis or below the x-axis. It's sort of facing the x-axis in some way. There's no tilt in either the positive y-axis or the negative y-axis, and so we would expect no normal component in the y direction. Okay, so let's write out the equation of the plane corresponding to this normal vector through the point 0, 0h, which is the tip of the pyramid. We'll take 4h over a times x minus 0 plus 0 times y minus 0 plus 2 times z minus h, and all of that's equal to 0. Of course, the middle term we can ignore, and simplifying this a little bit, and let's solve for z, we get 2z equals 2h minus 4h over a. There's a common factor of 2, z equals h 1 minus 2h over a, like that. I think we're good. Yep, that looks good. Now we're going to integrate over this little region and multiply by 8 just like we did in the previous problem, and we're going to use the same order of integration, dz, dy, dx. So the volume is going to be 8 times the triple integral of 1 dz, dy, dx. Z is going from the xy plane, z equals 0, up to the equation of this plane. I've dropped an x somewhere, haven't I? Yes, right here and here. Okay, so I have to be really careful here, and I think there's no h in this. Apologies. 2 x over a. Does that look right? I think we're good. So z goes up to h times 1 minus 2x over a. Y is going to go from, well, y, parallel to the y-axis, we start down here at y equals 0, and we end up on the line y equals x, so we're going 0 to x. And last, take that, squash it down onto the x-axis, and the limits there are going to be 0 to a over 2. If we go over to Sage, and I've already plugged this into Sage just to save time, we of course have to declare these new parameters a and h. I'm going to assume that they're both positive, which is a safe thing to do because a is a side length and h is a height. And, you know, it makes life easier for Sage. We integrate the inner, which is just 1, with these z limits. The middle, which is the inner with respect to y, going from 0 to x. And finally, the outer, which is the middle with respect to x, going from 0 to a over 2. And we run this, and we end up with 1/24 a squared h. So this integral, the integral itself, is 1/24 a squared times h. And of course, 8 over 24 is 1/3. So we get a squared h over 3. I think that's what we were looking for. Yeah. A squared h over 3, a squared h over 3. So we're good. Okay. So that's an application. The last one is a question from physics. If the charge density at some point x, y, z of a solid E is given by the function rho, then the total charge inside the solid is defined as the triple integral this. Assume that the charge density of the solid is assume that the charge density of the solid E enclosed by the paraboloids blah and blah is equal to the distance from an arbitrary point in the set to the origin, and set up the integral that gives the total charge. All right. So what we're given here is that the density function rho of x, y, and z is equal to the distance from a point to the origin. So that's just the square root of x squared plus y squared plus z squared. Square root like that. So that's the integrand. Now the paraboloids, it's maybe not obvious, but you may remember that paraboloids look like this in 3 dimensions. They kind of come up and they grow sort of like they're like parabolic bowls. Now these paraboloids are oriented in the x direction. We've got a paraboloid opening along the positive x-axis but shifted back along the x-axis by 5 units. So what that would correspond to is, and my art here is going to really suffer, I think, but let's give it a shot. So we have this paraboloid that's opening along the positive x-axis, but it's shifted back. So it's going to go something like this and like this. And this is -5. Okay, so that's this paraboloid. The other paraboloid is the paraboloid's flipped over because it's multiplied by a minus sign and then shifted 5 units ahead on the positive x-axis. Maybe I'll sketch that in a different color. So here's 5 units ahead, and that's going to open up kind of like this and like this, and then have this sort of circular cross section like that. Really, really hard to visualize, but you can possibly imagine that it's these two guys together and they join right here along the YZ plane, and they join in the form of a circle. So I think the wisest move would be to integrate in the x direction. So that means a line that's parallel to the x-axis, and it's going to start on this paraboloid and end on this paraboloid. This paraboloid is the one with the positive x squared and z squared. So let's start building this integral. We're going to go dx, and then honestly, looking ahead, I see that in the YZ plane, this region is going to be circular, so it doesn't really matter. Maybe we'll do dz dy. Dx is always going to start on this, the black paraboloid, so it's y squared plus z squared minus 5, and end on the blue paraboloid, 5 minus y squared minus z squared. Once we've dealt with that direction, we collapse the whole thing into the YZ plane. So doing that should simplify the artwork, if nothing else. All right, and we're looking at some kind of circle in the XZ plane, sorry, the YZ plane. Question is, what's the radius of that circle? That's going to help us figure out the remaining limits. Well, what we're talking about is essentially what we get by, say, taking the trace of the blue paraboloid with the YZ plane. We can get that by setting x equal to 0. If we set x equal to 0 here, we get 0 equals 5 minus y squared minus z squared. So this is the trace of the paraboloid in the YZ plane, and that's the same as setting setting x equal to 0. Doing that, we get 0 equals 5 minus y squared minus z squared, which you may recognize as the equation of a circle. Y squared plus z squared equals 5. That's a circle of radius root 5. Great. Now, we said that we were going to integrate with respect to z next. Z we're using blue for. A line segment that's parallel to the z-axis is going to start. Let's solve for z over here. It's going to start on minus root 5 minus y squared and end on plus square root of 5 minus y squared. All right, last step, we take this domain in the YZ plane and we squash it down onto the remaining variable, which is y. Y we're using green for, and that's going to go from minus root 5 up to root 5, and that is up. I should be careful. That is, we're not doing volume here, we're doing charge density. So we don't want to put a 1 in here, we want to put rho in here, like that. And this is charge, the total charge. Okay? Again, this is probably a really challenging integral, so you would want to jump over to Sage if you were asked to compute it. But the key here is we were asked to set up the integral. So we've done that. All right, let's do a quick overview of the exercises here. In exercises 191 through 210, 191 through 210, at the end of the section here. So that's starting here and going all the way down to here. I want you to focus on setting up these integrals and understanding the setup. Don't worry too much about the evaluation. If it looks simple, it's good practice. Try your hand at evaluating, but if not, just leave it alone or jump over to Sage. You should also note that exercise 196 and 204, I found them to have errors in them, and I've sent a message to the textbook authors. Do a broad selection of the remaining problems, and when you feel like you're ready, go ahead and take the assessment on Chapter 5, Section 4 in WebWork. Thanks.